Hello everyone, welcome back to SimplyCam. So today we are going to build a turbo expander and NGL fractionation plant model. So in this video we will use LNG exchanger unit operation to simulate a multi-pass heat exchanger. The liquid produced from the inlet hydrocarbon will feed into a fractionation section consisting of a pair of distillation column for liquefied gas recovery. The process is a turbo expander plant where LPG product is obtained from a feed natural gas stream by cooling, expanding, separating, and distillating the condensed liquid. The remaining gas is then recompressed for export. So let's start the video. So first we will set up the turbo expander. So first start the new case, then start to add the then add the component list. So the component list is a very big list. So I will pause the video here and I will add the all component and then you can edit. So here we can see methane, ethane, propane, ibutane, n-butane, i-pentane, n-pentane, n-hexane and n-heptane and n-octane. So we need all these component. So just select all this and add, and also we have to add nitrogen, we have to add CO2, and the last one is water. So this is the component list: nitrogen, CO2, methane, ethane, propane, ibutane, n-butane, i-pentane, n-pentane, n-hexane, n-heptane, n-octane, and H2O. Now go to the fluid package. So in this video we are going to use Ping Robinson as a fluid package. Select Ping Robinson. Now go to the simulation. So first add a material stream, open it, change the name to feed mix, temperature will be 22 degrees Celsius, pressure will be 3500 kilopascal, and the flow rate will be 4145 kg mole per hour. Now go to the composition, click edit. So the nitrogen composition is 0.0108. So here is the mole fraction of all component. Add all this component mole fraction and then click OK. Now the feed is completely defined. Now the feed is completely defined. So before sending the feed mixture onto the turbo expander and fractionation section, it would be wise to attempt an inlet separation to knock out any produced water and as much liquid condensate as possible. So to perform this separation, we will apply the standard S-pen IC's three-phase separator. So go to the separator, add three-phase separator, open it, name as inlet shape. So the inlet will be feed mix, vapor product will be inlet shape wave, light liquid will be inlet shape liquid, and heavy liquid will be inlet shape water. So this is defined. Now we will going to add the LNG heat exchanger. So this is multi-pass heat exchanger, which is also known as liquefied natural gas exchanger. So the LNG exchanger allows for multiple hot and cold stream, while the heat exchanger model allow only one hot side stream and one cold side stream. So add the LNG exchanger, open it. So first inlet stream will be inlet shape wave, and the outlet stream will be 1A, and the pressure drop is 20 kilopascal, and the fluid will be hot. Second inlet stream is stream name as Seven. The outlet stream will be 7A, and the pressure drop will be 20 kilopascal, and the fluid will be cold. Now add another side. The stream name will be 9. Outlet stream will be 9A. Pressure drop will be 20 kilopascal, and the stream will be cold. So here we define the inlet stream for the heat exchanger. So that exchanger design method is used to split the heating curve into intervals rather than simply considering the endpoint. So the number of intervals is set in the exchanger details table. So here these are the parameters. We don't need to change any of these parameters. Okay. So the and here we can see specs. Okay. So the degree of freedom analysis, degree of freedom analysis. So 6 is there are 7 unknowns and one c- constant so far. So we will add two extra specification in addition to the default heat balance specs. Okay. So now click on the add. So the first specs will be cold, name is cold out sim. Type will be delta temperature. Positive stream will be 7A, and the second stream will be 9A, and the specs will be value will be 0. So it means that temperature difference of stream 7A and stream 9A will be 0. It means that temperature will be same for the both outlet. And now we will add another specs, name is approach temperature. So in the type we will select as minimum approach temperature. So in these specs, we try to set the overall minimum approach temperature in the exchanger is 10 degrees Celsius. So the pass will be overall and the specs value will be 10. So here two specs are selected. Make sure the active box is selected for both of these two new specification. So by adding two new specs, the number of degree of freedom is reduced to 4. Later, when more of the flow sheet is built, these 4 degree of freedom will be used up and the exchanger will have enough information to solve. For now, we will leave it this way and will continue to build our simulation. So now add a cooler. So drag the cooler, open it, name as E100. So here inlet will be 1A, outlet will be 2, and the energy stream will be Q100. Now go to the parameter. Here pressure drop will be 20 kilopascal. Now here we can see the duty is unknown. So for the calculating the duty, we have to specify the outlet temperature of the stream 2. So the outlet temperature of the stream 2 will be minus 62 degrees Celsius. So okay, close this. Now add a 3-phase separator. Open it. Name is V100. Inlet will be stream second. Vapor product will be stream 3. Light liquid product will be stream 4. And heavy liquid will be wastewater. Close it. Now add a expander. Add a expander. Open it. Here inlet will be stream 3, which is coming from the separator. Outlet will be stream 5 and energy stream will be QK100. Now go to the worksheet. The temperature of stream 5, sorry, the pressure of stream 5 will be 2800. Pressure will be 2800 kilopascal. So here we can see the expander is completely specified. Close it. Now add a two-phase separator. Here inlet stream will be stream 5 and vapor outlet would be stream 7 and liquid outlet will be stream 6. So the liquid from the first separator, which is V100. So liquid from the first separator is placed down to the same pressure as the expander K100 outlet. So when the simulation is manipulated later, the turbo expander outlet pressure is one of the process parameter that will be changed. Hence, it makes sense to link this parameter with SPN HYSYS. Okay. So now we are going to add a wall. Add a wall. Open it. Namely, so the inlet will be stream 4 and the outlet will be stream 8. Okay. Now close it. Now we are going to add a set icon. Install a set icon. Okay. So open it. Install a set icon. Put it here. Open it. So here targeted object variable will be stream 8 and the target variable will be the pressure of the stream 8. Okay. And the source will be stream 5. Now go to the parameter. Multiplier should be 1 and the offset should be 0. Close it. You should save the flowsheet so you don't so you can use it later or you don't lose it. So now we are going to add a fractionation column. So the inlet condensate stream still exists as its feed condition while stream 8 has been refrigerated and brought to a lower pressure. The inlet condensate also need to be brought to the proper thermodynamic condition. So first we will add a cooler. So add another cooler, open it. Name will be E200 and the inlet will be inlet safe liquid. Outlet will be 10 and the energy stream will be Q200. Now go to the worksheet. Temperature of the stream 10 will be minus 85 degrees Celsius and the pressure of stream 10 will be 2790 kilopascal. Now it is completely defined. So the outlet which is coming from the first separator, which is inlet separation liquid, means this is liquid, which is, so we are going to cool it down to the minus 85 degrees Celsius. Okay. So here we need to add a material stream. So add a material stream, name it as 11. So this will be used to represent the demethanizer column bottom liquid product stream. So we will use it there. Okay. Now we are going to add another set. Add another set. Open it. So here our targeted object is targeted stream is stream 11, and the object is the pressure of the stream 11. So select it, and the source will be stream 5 only. Okay. So now we are going to add another set. Open it. So it will control the pressure of the stream 9. So pressure of the stream 9 with the source of stream 5. Now go to the parameter. So we are going to use this set in a such way that the stream 9 pressure is 35 kilopascal less than that of stream 5. Stream 9 pressure is 35 kilopascal less than that of stream 5. So here offset will be minus 35 kilopascal. Okay. Now close it. Now we are going to use a column. So here we will use reboiled absorber. So go to the separator, search for reboiled absorber. So this is reboiled absorber. So we are going to use this. So add the reboiled absorber, open it, name it as demethanizer. So here the number of stages will be 10, and the top stage inlet will be stream 10. Optional inlet stream will be stream 8, which is going to enter at the stage number 2nd. So the overhead vapor liquid outlet will be stream 9, and the bottom will be stream 11, and the reboiler energy stream will be Q102. Click on the next. Click next. So since the product stream pressure have already been defined via the set operation. Okay, so that's why the pressure profile page automatically picks these values. So now click the next to continue. So these values are optional. So click next and click done. So now this is the monitor or design page of the column D methanizer. So first close it. First add a energy stream. Okay, add energy stream. Open it and title this energy stream as site duty. And specify a heat flow of 3.3 multiply by e to the power 6 kilojoule per hour. Now close it. Open the demethanizer column. Now connect the site duty stream to the stage 4 of the main tower. Site duty to the stage 4 of the main tower. Okay. Now go to the monitor page. Since no value were entered for the specs in the input expert, no values are present here. Since the column has fully defined feeds, the pressure are known, and one space specs is activated. So the degree of freedom, it's showing 0. So now we are going to specify a value of 800 kilogram per mole kilogram mole per hour for the overhead product rate. So specify the 800 kilogram mole per hour. Now click the run button. Okay. So here we are going to add another specs. So click on add specs. Select the component vapor pressure. So it is the component vapor pressure spec. Click add spec. Name as BTMS RVP. The stage will be reboiler. Type will be red wave pressure. Phase will be liquid. Specs value will be 1380 kilopascal. So deactivate it. Activate this value. So here we add the new specs. Bottom reboiler vapor pressure as 380 kilopascal. Deactivate the overhead product rate and activate the bottom reboiler vapor pressure, and the column will be converged. So close it. Save your case. Now the stream 11, the demethanizer bottom will now be further proceed. A de-ethanizer column remove ethane and lighter component in the overhead row, while propane and heavier hydrocarbon are drawn from the bottoms. So now we are going to add another distillation column. Now add another distillation column. Open it. Name it as de-ethanizer. Number of stages will be 16. And the inlet stream will be stream 11. The condenser will be full reflex condenser. Overhead product will be stream 12. Bottom will be stream 13. Condenser energy will be Q103. And reboiler will be Q104. Click next. Click next. So the condenser pressure will be 2730 kilopascal. Condenser pressure drop will be 20 kilopascal. Reboiler pressure drop will be 0, and the reboiler pressure will be 2785 kilopascal. Click next. Click next. And the reflex ratio value will be 3. Click done. This page will open. Now go to the monitor. So here you can see the degree of freedom is 1. So we are going to add a specs. The specs will be column component recovery. Add specs. Name it as C3 recovery. It will be drawn from C13, sorry, 13 at column 2, and the specs value will be 0.95. The component will be propane. close it, activate the C3 recovery and reflex ratio, and run the column. So the column is successfully converged. Close this, save the flowsheet. Now the simulation is almost complete. So the two product gas stream from the LNG exchanger. From the LNG exchanger, the two product stream is 7A and the 9A. Okay. So now we will mixed and recompress these two product gas for the export. So for mixing, we are going to add a mixer. So add a mixer, open it. Inlet will be 7A and the 9A. The outlet will be stream 14. So these are the outlet. Now we are going to add a compressor to compress the outlet of the mixer. So add a compressor, open it. Inlet will be stream 14. Outlet will be stream 15. Energy will be QK 100. Now we are going to add one last compressor. So add another compressor. Open it. So in this cell, inlet will be 15. Outlet will be sales gas. Energy will be QK102. And now go to the worksheet. And we want the outlet pressure of sales gas as 6000 kilopascal. So this is the whole flow sheet. So there are two compressor specified differently. K101 has a fully specified inlet stream and a specified duty calculated via expander K100. So we are use this as a energy stream in compressor 101. While the export gas compressor, which is K102, is a fully specified inlet stream and a specified outlet stream. Okay, so now you can see in the wastewater stream, go to the composition, you can see the mole fraction of the water is the highest, which is 0.9986. Okay, now go to the sales gas, go to the composition. So in the sales gas, the mole fraction of methane is the highest because we want to sell the methane gas. Now go to the demethanizer. Click on the material stream 9. Otherwise, first click on the material stream 11. Check the composition. So here you can see ethane, propane, and the other heavy component are there in the material stream. That's why Here we are using the de-ethanizer to separate the ethane and the other heavy component. Now click the stream number 12, go to the composition. So here you can see the most of the ethane is coming from the top of the column because we want to separate the ethane and the other heavy component. So here you can see the mole fraction of ethane is 0.944 in the upper stream of the de-ethanizer. If you see the lower stream, go to the composition. Here you can see the ethane composition is very low. Here propane, ibutane, n-butane, i-pentane, n-pentane, and the other heavy components are there in the stream number 13. If you see the stream number 9, which is coming from the demethanizer, so click on it, go to the composition. So you can see the here the mole fraction of methane is 0.9547. Means most of the methane is coming out from the stream 9 from the demethanizer because we are using the demethanizer for separating the methane from the stream gas which is coming at the stream number 8. In the stream number 8 you can see the composition of methane, ethane, propane, all are there. Methane is 0.46, ethane is 0.31. So we want to separate the methane from the ethane. So we can use the methane in the LNG exchanger, and from the LNG exchanger here in the 9A stream we are getting the methane, and then we are in the 7A stream we are also getting the methane. So after that we are mixing these two methane 7A and 9A. We are getting the stream number 14. In this the methane composition is 0.9212. Then we are going to compress this gas for two time, and then we are getting in the sales gas the methane composition is 0.9212 with the pressure of 6000 kilopascal at the temperature of 84.99. So we are going to sell this gas, and the 7A which is coming from the separator. Thus separator is separating the stream number 7 which is coming from the out of the separator which has 0.8973 mole fraction of methane, and the bottom of the separator which is stream 7. So stream 7 you can see methane, ethane, propane all are there. So again we can use this stream, we can add this stream to the demethanizer to again separating the methane and ethane from it. So we can use it again. So here from the three-phase separator, one is wastewater, second is stream number 3. The stream number 3 is the most of the methane. Stream number 3 is going to the compressor, and then it is going to the separator. From separator we are separating methane and the other stream. This stream can also go to the demethanizer, and the other stream from the three-phase separator which is stream number 4. Stream number 4 also have same the methane, ethane and all, and we are then going to we are sending this stream using a volt to the demethanizer. Instead of stream 4, we can also send the stream 6 to the demethanizer to separate the methane from it and the other gases. So these other gases can also send to the deethanizer, and from this the ethane gas and the other heavy component will be separated. So this is the whole flow sheet. You can set to the auto position. It will be auto position, again set to the auto position, zoom it, now set to the auto position. uh, this is all mix up, so you can Set it according to you. Mine is not working properly. I don't know why. But yeah, this is the our flow sheet. So yeah, this is the our flow sheet. You can set it according to you. So thank you for this video. In the next video, we are going to modify the inside of the distillation column. So for the next video, you should save this case in the system so we can directly use this case for the next video. Or otherwise, if you are new in the next video, then you can watch this video to simulate the whole flow sheet. And thank you for watching the video. We will see you in the next video. Till that, be happy, stay tuned, and learn always something new. Bye bye.